All right, so I think we are now live once again. So hello everybody, welcome back to another edition of Quarantine Thermo. Today I'm very pleased to welcome Professor Irene D'Amico from the University of York. And so this should be a really interesting talk. So Irene is an expert in many different aspects of condensed matter physics and many-body physics, and also quantum thermodynamics. Before I hand over to her, I'm just going to briefly do what I always do, which is just reiterate the format for any new viewers. So basically, Irene is going to speak for however long she likes, uninterrupted, and then we'll have a question and answer session at the end. So please do feel free to ask questions just by writing them in the YouTube chat window. You can ask them during the talk or at the end of the talk, and at the end of the talk I'll relay them to Irene, and we'll have a question and answer session then. So yeah, I mean, I think without further ado, I can start. So I'll hand over to you, Irene. You can take it away.
Okay, thank you very much, Matt, for the introduction, and thanks also for organizing this quarantine quantum thermodynamic series of talks. They've been a lifeline, as I was saying before. So I hope all of you can see the first slide of the presentation. As has been explained, I am going now to start this long monologue, looking at myself mainly. Okay, so I'm Irene D'Amico, and I will be talking about density and state metrics to measure adiabaticity at finite temperature. And this work has been done in collaboration with Ami Skelt, is part of her PhD work. Ami has very recently graduated. You can see she's very happy now. And well, I'm joking, she's usually very happy. And the PhD was funded by EPSRC, while I've done part of this work at the International Institute of Physics. As a tradition, I will start with an overview on what's going to happen in the next 40 minutes or so. I will, first of all, give some motivations beyond this talk. I will say a few words about the Quantum Adiabatic Theorem, or theorems, as should be most precisely said, and about the Quantum Adiabatic Criterion, which is defined at T equals 0, temperature equals 0. I will then pass on to some way of tracking, measuring adiabaticity beyond the Quantum Adiabatic Criterion, and for 0, and then I will start talking about the core of this work, that is the case of finite temperature. To do so, also, I will introduce a new finite temperature quantum adiabatic criterion. We had to introduce it mainly to give to people, to the reader, and also to ourselves, something more familiar to deal with when looking at the results with the metrics. I will then show numerical application of the method, and draw some conclusions. First of all, let me make a quick note about what I mean by adiabatic. I have here copied and pasted a sentence from Wikipedia, from the Adiabatic Theorem, that says that the term adiabatic is traditionally used in thermodynamics to describe processes without the exchange of heat between system and environment. Now, this is not the type of adiabaticity I'm going to discuss in this talk. What I will be discussing instead is the quantum mechanical definition of adiabaticity and processes. And so when I talk about adiabatic process, I will refer to a quasi-static process. A few lines, a few words about motivation. Well, I suppose the main motivation is really, as usual, curiosity. and some fundamental interest in trying to understand a bit better how systems behave, close or not so close to adiabaticity, especially because now in fields like quantum thermodynamics, there is a lot of interest in out of equilibrium system, and also in systems that are driven close to equilibrium, for example, in the case of quantum thermodynamics, because this may help reducing the entropy production or the quantum friction. In general, in a way, the adiabaticity is connected to a large number of fields and protocols. For example, in quantum computation, we have adiabatic quantum computation, but also adiabatic gates. The adiabatic theorem itself is connected to the Berry phase. And in general, adiabaticity or lack of it comes into play anytime we have a dynamics which involve a relatively complex spectrum with crossing, anti-crossing, and so on, which are typical, for example, of spectra for molecules or nanostructure, or even more complex many-body systems. So the questions which we will be dealing a bit during this talk are when does a system behave adiabatically? Can we also see how close or how far the system is from being adiabatic? And can we track adiabaticity? So can we look how the system is changing its level of adiabaticity, maybe coming back to adiabaticity if, for example, the protocol require my system to be adiabatic, a certain protocol require my system to be adiabatic during part of the dynamics. The type of systems I will be discussing numerically will be closed quantum system. So I will be talking numerically about closed unitary dynamics. In this case, I would like to underline that an adiabatic protocol is actually different from an equilibrium protocol. This picture here is taken from this picture here is taken from the thesis by Marcel Herrera, and shows that in the case of a closed system dynamics, driven closed system dynamics, we believe that even if we start from a system at equilibrium at time equals 0, and we drive our system very slowly, so to satisfy the adiabatic theorem and having an adiabatic protocol, the state which we end up with is a state which is different from the equilibrium state of the system. This is because the weights in the mixture of states at time 0 have been decided by the temperature, of course, but also especially by the eigenstates of, eigenenergies by the spectrum of the Hamiltonian at t equals 0. And this will not correspond to the spectrum, the value of the eigenenergy at the end of the dynamics. And this energy here that the system would dissipate if put again in contact with the buff at time tau to go from the state at the end of the adiabatic dynamics to the equilibrium state is known as the residual lag, and is a measure of irreversibility, and it can be quantified by the Kullback-Leibler divergency. Okay, so in an adiabatic protocol, we have no quantum friction, but we have in general a residual lag if the system is closed. Let me now spend a few words on the quantum adiabatic theorem, as nicely stated in the paper by by Evron and Elgart. I will cite from that paper, there is no single adiabatic theorem. Different adiabatic theorems focus on different aspects of the problem. So in general, when we talk about an adiabatic theorem, what we mean is that the quantum system starting in an eigenstate will remain in the corresponding instantaneous eigenstate of the Hamiltonian if the system is driven slowly enough. The adiabatic theorem in its first formulation was derived by Born and Fock in 1928. The first formulation dealt with the discrete-only spectrum, but already was considering not only a spectrum with gaps between each and every eigenstate, eigenenergy, but also spectrum with linear crossings between key eigenvalues of the spectrum. About 30 years later, Kato has discussed the case in which we have a degeneracy in the discrete part of the spectrum, and also the possibility of having part of the spectrum that is continuous. And then it has been, the presence of energy bands have been included in the adiabatic theorem, and in 1999, this is the paper I was citing before, the adiabatic theorem has been formulated without reference to a gap condition. This paper is really nice also in the description of the various flavors of the adiabatic theorem. I would like also to mention this very recent paper is on the archive by Lin, Aristova, and Likovsky. That actually formulate the adiabatic theorem for closed quantum systems at T, temperature greater than 0. I want to stress that the work I'm presenting and this paper here have been developed independently. Now, all is good when we have some mathematical theorem telling us that the conditions that adiabaticity is possible. However, we would like to, given a certain type of dynamics, however, we would like to have a bit more information on what is the type of dynamics that we actually need for preserving adiabaticity. And for this, we would like to have conditions or figure of merit or quantities that we can easily or relatively easily calculate either by hand, but more probably with our computers. So the adiabatic behavior is usually checked against what is known as Quantum Adiabatic Criterion. Before I call it Adiabatic Quantum Criterion, I will go on with Quantum Adiabatic Criterion from now on, Q-QAC. This is at T equals 0. And this says that, in general, the dynamics should be adiabatic if the ratio between the matrix element, between the derivative of the time-dependent Hamiltonian and so the matrix element between the ground state and all the various instantaneous excited states, divided by the modulus square of the difference in the corresponding eigenenergies is much less than 1, and this should be for any excited states and at any time. Now, already for certain systems, the sufficiency and validity of the quantum adiabatic criterion have been questioned. Here there are some reference paper in relation to this. So we really would like to go forward from here also, because this is a criterion at temperature equal to 0. And if we think about the expression of it, we see that in general, if we are dealing with large Hilbert spaces, it's become difficult to calculate. It becomes numerically quite cumbersome to calculate it. We usually people truncate the number of states on which is calculated. So usually M is just, very often M is just the first excited state. And often is calculated just at the initial time to have an idea of how the dynamic would develop. If we think about large many-body system, well, we have very complex instantaneous spectra. We will have many crossings, anti-crossing. So if we are going to calculate numerically this object with a denominator that will tend to go to 0 at crossing or very narrow anti-crossing, clearly we can have numerical instability. And in general, it's been highlighted that there can be this small denominator problem when this matrix element, this matrix can be different from 0. This particular expression here is also not suitable if we have a continuous spectrum. And as you will have noticed, it depends at most from the derivative of the time-dependent Hamiltonian, which means it doesn't really have much memory, so it's a quasi-Markovian type of measure. In addition to this, there are the usual problems that are there with many-body systems. So the spectrum, as I said also before, is quite complicated. It may be partly discrete, partly continuous. In general, computationally is very complex to obtain exact or good solution for the state of the system, even for systems that are not very big, very large, just few particles. Even if we have this solution for the exact many-body state, well, what do we do with it? The kind of information that we have in a many-body wave function is, in complexity, is enormous. I mean, a many-body wave function is a function at an instant of time of the position of all particles and spins in case in the system. So it's a very complicated quantity. How do I look at it? How do I even just visualize it? Because of all these issues, we think, and we are not the only one, that is worth it to think a bit beyond the quantum adiabatic criterion. And there have been some work done recently for many-body pure states. So we are talking about temperature equal to 0. And for example, in 2017, Likovsky and co-author have discussed, which is have derived an explicit condition for checking adiabaticity in large, checking and maintaining adiabaticity, so a criterion that can be calculated numerically for adiabaticity for large many-body system. So system which undergo the so-called orthogonality catastrophe, where the fidelity between the time-dependent instantaneous eigenstate of the system and the adiabatic state of the system. So the instantaneous ground state of the system, we are at T equals 0, and the original ground state vary very much for small variation of the parameter that is driving the Hamiltonian. We have also worked together with, again, Ami and Rex Godby on using metrics for characterizing the degree of adiabaticity in system, quantum systems, continuous quantum system, and many-body systems. Again, in 2018, again, Likovsky and co-authors have also proposed in adiabatic fidelity as figure of merit for checking adiabaticity, specifically for this system here, a 1D impurity fluid system, where the fidelity is the fidelity between the current system state and the instantaneous ground state. The fidelity is not a metric, though it is connected, for example, to the Behaviour metric. So the work I am going to present, this is the reference, has been recently published, is aiming to characterize adiabaticity and the level of adiabaticity during the dynamics for quantum systems, and the method works both at T=0 or finite temperature. We base the method on metrics, which can be then applied to many body systems of any size. They can be systems that are over continuous, that are continuous in space or are defined over a discrete lattice. The spectrum can be continuous or discrete, and as I said, may work at T=0 or finite T, finite temperature. And in doing so, we also, for comparison, define a temperature-dependent quantum adiabatic criterion. One of the things that has been a bit of a turning point in this work is, well, in this work with metrics, is really something stemming from, inspired by density functional theory. Density functional theory, in its various incarnations, establishes a one-to-one correspondence between the state of the system and the corresponding local particle density. Here I've been very vague on the state of the system. The original theorem by Onenberg-Kohn was defined for ground states, but then in the static system, but then by Lung and Gross extended the theorem to systems depending on time. And this was also extended then to lattices depending to system defined on lattices, so discrete with time dependence. So because of this one-to-one relationship, the idea is, okay, the metric for the state of the system is nice, but is based on the state of the system, and so the state of the system may be something very difficult to calculate. So we actually use the particle density instead. The particle density is in principle unobservable, and also is much easier to estimate than the corresponding many-body state, for example, using density functional theory methods. And what we will show is that indeed this is possible, at least up to the systems, and with the caveat that I will be discussing later. In general, let me just recap the properties of metrics, so to be sure that we are on the same page on what I mean when I talk about metrics. In general, a metric space is an ensemble of elements in which I can assign to any two elements a distance. But this quantity, the distance, has very specific properties. First of all, the distance is positive and is equal to 0 only if the two elements are exactly the same. I have also the property of symmetry, so the distance between A and B is the same as the distance between B and A. And then, very importantly, because it's often used, there is the triangular inequality. that says that given three elements in my metric space M, A, B, and C, the distance between A and B is less or equal to the distance between A and C plus the distance between C and B. And now there is only a slight little problem. That is, given a set of elements, usually one can assign to the same set of elements various different metrics. So some of them are trivial, are really trivial. So if we want actually to have physical information from a metric, better we make sure that the metric we choose is able actually to convey this information. So the metrics that we choose are what we now refer to as natural metrics. These are metrics that can be derived from conservation laws. And in this sense, because they have this content, this physical content, they're actually able to provide physical insight into the systems. We have used them for various works so far. For the state of the system, this metric is the Behaviour metric, the Behaviour distance, which is defined in general in this way, where rho and sigma are system states. And for the local particle density, the natural matrix for the density is 1 over n, the integral of the modulus of the density for system 1 calculating at R minus the density for system 2 calculated at R, all integrated over the whole space. In addition to the natural metrics, on which we were already very confident because of all the work we've already done on this, we have decided also to look at to analyze if the trace distance can be used to actually define and track adiabaticity in a system. And this is because the trace distance is very much used in the community and is considered as a best measure to distinguish operationally two quantum states. And indeed, this is what we want to do. I mean, if you want to know if your system is adiabatic or not, you want to know if and how much is different from the corresponding adiabatic state. So we thought, indeed, this was also a good candidate for a metric for tracking and checking adiabaticity. As I said already, but I will repeat it, we focus on the particle density metrics, as we know that we have one-to-one correspondence between the driven system many-body state and the corresponding particle density. I suggest this book for time dependence density functional theory by Carsten Ulrich. This treat the system at t equals 0. This is the Runge-Gross theorem is at t equals 0. At t greater than 0, there are now more and more developments in density functional theory, also stimulated by all the work that is done currently also with quantum technologies. So in this sense, the idea is, following this theorem, to shift the focus from the state of the system, the quantum many-body state, to the corresponding local particle density. And as I said, we used them already successfully to study various systems, and in particular also the relationship between wave functions and corresponding particle density within the fundamentals of density functional theory. Just a quick reminder of the general problems with many-body systems. They are complicated, lots of crossing, anti-crossing in the spectrum, complicated spectrum. Spectrum can be discrete, continuous, computationally are very hard. And even if we get the many-body time-dependent wave function. What do we do with it? How do we distill relevant information? And what do we do at temperature greater than 0? And what I will be arguing is that the natural metrics are a possible solution to this, or at least part of these problems. They can be applied to continuous and discrete spectra, both at t equals 0 and t greater than 0. They contain memory by construction because they are based on the one that we will use. They are based on the time-dependent many-body wave function or the time-dependent local particle density. And they're nice because they're just a number, so we can actually visualize them very easily. They're good for distilling information, if you know how to ask the question nicely, I would say. And again, the particle density and its metric is relatively easy to calculate, even for large systems, for example, via EFT methods. So before showing you the numerical results, basically an application of the method, how you would apply this method, let me just introduce a couple of concepts that I will use. The first is the adiabatic threshold for the system state metric. So when I was talking about the quantum adiabatic state, I had a quantity such that if that quantity was much less than 1, I would say my system is adiabatic. So I want something similar in the case of my metric that answer this question: when can a system be considered adiabatic for all practical purposes? And in this case, it's important that the metrics we choose are metrics with a maximum, a well-defined maximum, because in this case, we can quantify this threshold based on the maximum of this distance. Basically, what I'm saying here is that the threshold below which I will declare my state to behave adiabatically, when I calculate the distance between the ground state or the adiabatic state corresponding to the mixed state at finite temperature, and so the distance between this and the current many-body state at time t. So when this distance will be less or equal to the maximum of my distance divided by 10. Clearly, I could choose a different threshold, tighter or looser, it's up to me. Divided by 10, what does it mean? It means that this distance is an order of magnitude less than its magnitude, that is maximum. And so it's a good way of saying it's small with respect to its maximum. And we see from the results that this is a good threshold. I will show that. Now I need to do the same for the particle density metric. However, I don't want to define another arbitrary threshold, because then I would have two arbitrary thresholds, possibly independent from each other, and this is not good. So I want to define the adiabatic threshold for the particle density metric based on the adiabatic threshold for the state metric. And for doing so, I exploit the fact that we have observed that there is a quasi-linear relationship, here it is, between the density distance between the ground state slash adiabatic state at t equals 0 and the corresponding ground state slash adiabatic state at t, and the corresponding Behaviour distance for the states. So I can measure, I can calculate, estimate, sorry, this linear coefficient m here relatively easily by simply estimating it from 2 or 3 values along these lines at corresponding time t. So numerically, this is relatively cheap to calculate. And then starting from this relationship, I can then derive, I will not show the demonstration is in the supplemental material, a upper bound for the threshold for the particle density matrix with respect to the threshold for the adiabatic line, for the threshold for the state matrix. So this is important. Only delta rho is chosen arbitrarily according to how tight or how loose I want to be with defining my adiabaticity, but delta n is not chosen adiabatically, it's fixed 1, at least the upper bound is fixed 1 once I have chosen delta rho. And let's now demonstrate the method. So we have chosen to study inhomogeneous driven fermionic Hubbard chain at half filling. We have open boundary condition. This is the Hamiltonian hopping term, on-site Coulomb repulsion, and applied on-site potential. This is the part that will be depending on time. The type of driving that we have chosen is a potential difference uniformly distributed across the chain, which starts from a potential difference across the chain of 1J. J is my hopping parameter, is my unit of energy in for all the next slides, to a potential difference much bigger. So with time, I am tilting my chain, if you like, the potential of my chain, up to 10 times J. We do this calculation varying for 3 different values of the on-site Coulomb repulsion, no Coulomb repulsion, 5J and 10J. And also we do this calculation from 3 different values of temperature. Temperature T equals 0, low temperature 0.2 J over KBT, and what we refer to as high temperature. I'll show you what I mean by this in a moment, why I call it high temperature. That is to 5 J over KBT. So again, J is my unit of energy. And we will be simulated a closed system with at the beginning, starting from a thermal state. So I thermalize the system, I detach the bath, and then I start my dynamic by driving the system. So before you tell me it's only six sites at half filling, so only 6 particles and 6 sites, this is just part of the spectrum of the Hamiltonian. So the Hamiltonian, the overall Hamiltonian, under this condition, mz is equal to 0, is 400 by 400, so I have 400 energy levels and corresponding eigen states. At u equals 0, this is how the state, how the spectrum looks like. When I increase u, I see that something starts to happen with the spectrum. It starts to differentiate. And as I increase u further, I see the formation of bands. So discrete sets of energy states, which do group into bands. And the lower one is given by the states which are formed by single occupation basis states. So basically what I see here is the Coulomb repulsion between states where I don't have double occupation in the site, and states in which I allow one site here to have 2 fermions on the same site. And as you can see, here I start to see these bands forming. Here I'm basically having a transition, a precursor to the metal to mott insulator transition, and here I have indeed already the gap. So I have now a substantial gap between the 2 lower bands formed by these sets of discrete states, and this is the equivalent for a finite chain of a mott insulator. The bands bend because I'm driving the system. So I am basically I'm driving the system against this phase transition, because I'm driving the system applying an external electric field between the ends of the chain, and so trying to drive transient currents across the chain. Transient because I have open boundary conditions. So let me now, before showing you the numerical results, let me introduce what we have proposed, mainly for comparison, as temperature-dependent quantum adiabatic criterion. It is this object here. You will recognize within the parentheses formally the quantum adiabatic criterion at t equals 0. However, here we look at the maximum of this quantity, so the ratio between the matrix element between the instantaneous eigenstates m of t and n of t of the time-dependent derivative of the time-dependent Hamiltonian, and the square of the modulus of the difference between the corresponding eigenenergies. So we have to look at all of these ratios and look, so all n, all m, this time I cannot simply say n is the ground state because I'm thermal, I have a finite temperature, so I will have a number of states that are occupied, that will be occupied, and so I have to check my transitions, if you like, my possibility of transition between, not just between the ground state and all the rest, but also between all the excited state and all the rest. And as you can imagine, this can be quite tough numerically, especially if your Hilbert space becomes very large. So in order to take care somewhat of the fact that we have a temperature, so if we start from a thermal state, for example, the states that should be mainly occupied are the ones in the range of kBt from, or few kBts from the ground state, then I can also impose some cutoff on the search of this maximum in terms of the states, the values of n and m I look for. So this is the meaning of these conditions here. And in this temperature-dependent quantum adiabatic criterion, we are also including the treatment of degeneracy following the way in which this was done for t equals 0 by Irene and Ortiz in this paper. So first of all, now let me show you the results for this finite temperature quantum adiabatic criterion at 0 temperature, because I want first of all to show you how these quantities behave at 0 temperature. So we are looking at, as I said, 3 different values from u. For u equals 0, u equals 5j, this is the on-site repulsion, u equals 10, and also 3 different type of dynamics. So tau fast dynamics, tau equal only 0.5 of j divided by j, a medium dynamics, tau equal to 5 over j, and a slow, we see what slow mean, dynamic, tau is equal to 50 over j. And we see that the system seems to start for the fast dynamics from non-adiabaticity, and also for the intermediate dynamic, but then seems to recover somehow, according to this criterion, some adiabaticity, if I take the value of finite t. Nicely also, we see that indeed this criterion sees the transition to the quasi-Mott insulator, so it sees the avoided crossing that we have looked at before between the, in this case, the ground state and the lowest avoided crossing in the spectrum. And here, the fact that I have adiabaticity at the beginning depends on the fact, again, that the ground state tends to be isolated from the rest. So this is nice. We see this feature. But then we seem to go back to adiabaticity. Again, also at larger u, I see again a signature for anti-crossing. This is nice. I'm also questioning why the system would be non-adiabatic at the very beginning, because I'm starting from the actual thermal state. So what I see is that I have some problems with this criterion. And as I can already see, a lot of the problem is related to being able to track adiabaticity, going back, for example, to adiabaticity after the system was non-adiabatic. And this is an issue related to the fact that this quantity is basically Markovian. If we compare it now to the viewer distance, so our first metric, so this is what you've seen before. And here the dashed line is our adiabatic threshold as we had defined before. So we see that now, when I consider the viewer distance as a measure for adiabaticity, indeed I recover adiabaticity at short times, as I should expect. But also I see that once the system becomes adiabatic, at least in this case, it remains. It becomes non-adiabatic, it remains non-adiabatic. I don't go down to some kind of adiabaticity, so I have memory. And anyway, also this measure responds very nicely to our avoided crossings for both values of u. And again, memory, the system remains non-adiabatic indeed after the peak. I just want to point at this oscillation that you see here. This was something we discussed in this paper, and this is the most adiabatic scenario. It's a very long time for the dynamics. And what you see here is actually, even when you go very slow, your system will have some inertia in following the application of adjusting to your driving. So the adjustment to the driving is not instantaneous. So you will see this little oscillation with the time. And what is nice is that, again, the metrics are non-Markovian by construction, and this is crucial to actually be able to track adiabaticity with time. And let me now show you how the time-dependent metric for the density compared to the viewer's metric. So this is the viewer metric that you have just seen. This is the corresponding metric for the particle density. And you can see immediately that the two are indeed very close quantitatively, because now this delta n here is, again, the threshold. In this case, is the upper bound to the threshold that I have derived starting from the adiabatic threshold for the distance, for the viewer distance. And we see that indeed both metrics signal adiabaticity at the beginning of the dynamics. They respond to avoided crossing in a similar way. They remain non-adiabatic, so they show memory when the system has acquired this non-adiabaticity. And also we have the same tracking of this inertia to adjust to the applied field. Now, all of this is important to notice, because while I have a one-to-one correspondence at T equals 0 between the state, time-dependent state, and the time-dependent density, I don't have a one-to-one, cannot have a one-to-one correspondence between the two corresponding metrics. And so one could think that maybe the particle density metric is less sensitive, for example, to little variation of the field or to little of the spectrum. But actually, we see that this is not the case. And so, again, from this one-to-one correspondence, we have conjectured that the n can be used to measure and track adiabaticity, as we see dB, the distance for the viewer's distance, can do, and the numerical supports this. So let me now go at finite temperature. And I skip the intermediate temperature. The results for the intermediate temperature are in the paper, if you are interested in those. Now I'm trying to explain you why I claim that this temperature is a high temperature. This I'm showing back this spectrum that I've shown before. This is U equals 0, U equals 5J, U equals 10J. The energy scale on the y-axis is different. So here, for for giving a better visual information, I'm using this blue square to show you the value of KBT in all the three graphs. And so you can clearly see that in all the three cases, I have that my initial state, my initial thermal state will have significant weights in the mixture for a number of excited states. For example, for U equal 5J and U equal 10J, I will have that both lowest bands, in both cases, the lowest band will be well occupied by at the beginning of my dynamics. While if I think about my U equal 10 and the first excited band formed by 6 states, this is important, will be important later, this will be empty at, for practical purposes, will be empty at T equals 0. So we will have no weight on in the mixture on the states at T equals 0. So these are the results. Now I'm comparing directly at finite temperature and comparing directly the results for the T-QAC, the temperature, finite temperature quantum adiabatic criterion versus the results for the Behavior's metric. And again, I see what I've seen at T equals 0, that for U equals 0, okay, I see what I've seen at T equals 0, that the measure and this estimate of adiabaticity give basically opposite information. If I think of them as a way of tracking adiabaticity, this is U equals 0. I noticed that in both cases, I can see that I don't have yet energy crossing at small times, so the system remains adiabatic when U is equal to 10. And also again, when U is equal to 10, I can clearly see for both methods that the crossing here of the upper and lower band, the lowest and the band immediately above, is actually very well signaled. And so here I have a series of spikes, and here I have a staircase. So I want you to notice that indeed this staircase is formed by 6 steps, each signaling indeed the crossing of one of the states in the upper band with the lower band. So every time one of the states, which was unpopulated, I remind you, enter the lowest band, this is signaled by a step in my Behavior distance. If you think about that, indeed, the Behavior distance is set up for this because it's maximum when it's calculated against orthogonal states. So this tells me, okay, I have a kind of anti-crossing, I definitely see it. But if you think about population and the fact that your population, thermal population, has been defined at T equals 0, we will also understand that how big, in the case of a mixed state, the variation of the distance is also depend on how different the initial thermal population is for these initial states. And so because these were empty at T equals 0, and these were more or less homogeneously populated, we see that each one of this crossing is signaled indeed in a very similar way by a high in the step that is of the order indeed of dB max divided by 20, I have 20 states here in the lowest band. Instead, and this was quite interesting for us, what we realized is that the peaks that we have up here from the T-QAC actually do not differentiate in anti-crossing or crossing that are relevant or irrelevant to the system. So I'm losing all this precious information about how really my system is changing for a small variation of my system parameter, the driving parameter. Even worse, if I look at the case of u equal 5j, I see that my system here, when I look at the T-QAC signal strong non-adiabaticity here at t equals 0.05, so really up here, yeah, when I start to have the crossing between the two bands, but in the case of u equal 5, while instead, in the case of the pure distance, it's simply telling me my distance is gradually increasing, but these crossings are crossings, anti-crossings are between states which have similar thermal population, at t equals 0, so I don't see big jumps. So this information is completely lost when I take this as a measure of adiabaticity. And if I compare this to the particle density matrix, again, I see that also in the case of the local particle density matrix, Dn, all these important features that we have seen for the pure distance are indeed reproduced. And as I said, the agreement between at intermediate temperature between dBurs and the density, and with the T-QAC is similar to t equals 0, but with the staircase starting to appear, and of course missed by the T-QAC. Last set of results I want to show you. I said that we also looked at the trace distance because it should be an optimal way of distinguishing states. And indeed, what we see here now, we are comparing the results at high temperature between the Bure and the trace distance. And we see that indeed they are very similar with respect to their threshold. Remember, the threshold is defined with respect to the maximum of the state metric, which is different from the Bures and the trace. So again, they signal loss of adiabaticity for the same value of time, and they have the similar staircase structure that we've seen before. And as I said, the adiabaticity threshold for the Bure distance is different from the adiabaticity threshold from the trace distance, because while they are defined in the same way, here is the definition, the maximum is different. So we have very good quantitative agreement. So you can choose which is your preferred distance in this sense to calculate and track adiabaticity. This brings me to the conclusions. So we have introduced a method based on metrics, and you have really to choose the appropriate metrics to measure adiabaticity for the dynamics of many body quantum system at finite temperature, which is also able to track the adiabaticity level with time evolution. The results so far support the conjecture that the natural metric natural metric corresponding to the local particle density is also able to track adiabaticity and signal adiabaticity. We have derived an upper bound for the adiabatic threshold for the local particle density metric. But as you may have seen in some of the view graph, it would be nice to have a tighter bound to that because we think it's still a bit loose. Now, we have extended the quantum adiabatic criterion to finite temperature, but we are not claiming that this is a particularly good quantity to establish or track adiabaticity, as you've seen that it has problems which are similar to the one that have been highlighted for the QAC at 0 temperature. Importantly, the metric-based method is able to correctly signal the anti-crossing which are relevant to the system, because the quantum state significantly changes at this point in time. While this is a problem when one consider measures which are Markovian, basically, like the Quantum Adiabatic Criterion, or this extension to finite temperature. So this concludes my talk, and many thanks to all of you for your attention, and I hope there will be some questions. Merci. Thank you.
Thanks very much, Irene. So let me just bring back my video. So yeah, as always, we have plenty of time for questions. So guys, don't be shy. Please feel free to just write your questions in the YouTube chat window. But there's always a bit of a delay. So maybe I can kick off by asking a couple of questions. Okay, yeah. So one kind of obvious question that came to mind when you were showing these results for this kind of Mott transition was whether there is some kind of, so do these non-adiabaticity metrics show some kind of universal scaling, like Kibble-Zurek type scaling as a function of the protocol time? I would imagine that they should, right? I mean, you get these kind of peaks close to the QPT.
Well, we have been studying this transition using, actually using the trace metric, exactly this transition. The paper has just been published. It is also on the archive. And we argue that we try to argue that we see some scaling with system size, but because we see some size similarity when we look at how the distance behave when we scale the system in size. So we definitely signal the transition. I mean, it's a good signal for the transition. But the problem is we cannot numerically go to systems greater than 8 sites, 8 fermions. So
right.
We see something, but we cannot, and we know what the limit should be, but this is just some numerical hint, if you like.
But I mean, if you were to scale with so I was actually wondering about the scaling with tau. You know, I mean, so I get, of course, scaling with n is going to be super hard, but I would have thought that I mean, if you get a peak close to the QPT, I would have thought that the height of the peak will depend on tau, and this height possibly could have a universal dependence on tau. I mean, I would have thought, I mean, that, you know, the height of this peak should be somehow connected to the density of excitations that are being created crossing the QPT. So the Kibble-Zurek type argument should apply, I would have thought.
Now, it may be, we haven't checked that, but let me go to the, okay. So first of all, this is not a sharp transition, okay, because it's this finite system. As you've seen, the crossing of the, first of all, they are not simply two states as you would have in the, I mean, if you go to the thermodynamic limit and says n tends to infinity, this band would shrink, okay, to not be there would not be a band with this state. So you would have a sharp transition between two level to crossing, real crossing. In this case, you have the crossing between bounds. That is what I was trying to show here. Okay, so first of all, it's not a sharp transition. And the second, the parameter that gives the transition is u. Okay, and here we are not varying u really. So maybe for seeing what you are looking at, maybe one would have to vary u. More than vary tau. I mean, for fixed tau, you would have to vary u, I think, for seeing what you are suggesting.
Right. I mean, I guess what I'm saying is sort of, I'm kind of implicitly assuming that there is some transition as a function of the electric field strength. Of course, I don't know if there is actually, but I mean,
no, the
but it looks like there is because you have I mean, it looks like there is.
Okay,
Sorry.
the multi-insulator transition is driven by the
U over J.
many-body coupling
Sure.
by U
Yeah.
over J.
So this is maybe not a Mott transition, but okay. Anyway, I mean,
the thing is, you have a competition between the application of the electric field, which is contrary to the transition because tends to create current, so to oppose the freezing of the system.
Yeah.
And the increase of U, and so the freezing of the system. And so we chose this particular dynamics exactly because you have this competition. So what you see is quite interesting from the physics point of view. But this is an interesting question. And yeah, no, we haven't checked if we have any scaling with respect to the high of the peak of a peak with respect to tau. This we haven't done. So.
Okay. All right. Thanks. Okay, so well, maybe I can ask another question. But yeah, please don't feel shy, guys. Feel free to ask any further questions. So, one thing I was wondering is, I mean, of course, the particle density contains, exponentially less information than the many-body wave function, and of course, that's a huge advantage as you were talking about. Are there any situations that you think where you really wouldn't be able to detect non-adiabaticity at all by looking at the density? Because I mean, there's lots of things like coherence, spatial coherences, and so on are not captured by this at all, right? So
let me correct you on one thing.
Okay.
The core, so correct you. I mean, there are hypotheses, but the core of density functional theory is actually that the amount of information is the same because there is a one-to-one correspondence. Okay, there is a one-to-one correspondence between, in the case of the Runge-Gross theorem, between here I've done it for the potential, sorry, between the state of the system. So you could read here psi of R and T, of psi of R1, R2, R3, etc., in time, and the density. So you have you have fixing the interaction between the particles. You have a one-to-one correspondence between the external potential, the state, the many-body state, which looks with plenty of more information, and actually the particle density. So the key point of density functional theory is exactly that you can use the density, in principle, to calculate not just ground state properties, but even excited properties of the system. Now, being able to calculate that is a different story. And as I said, most of the theory has been developed at T equals 0, while at temperature equals 0. While at finite temperature, they are still working on it. But this is why we were so keen into working with the density, because we actually expect to be able to see all the features. You can also look at the fidelity of the density, for example, and you can see that it will signal all sorts of things. We have a paper on the archive about that, but also somebody else work with the fidelity on the density. So it seems with much less information, but actually, taking care of, the fact that DFT apply to the system, but applies to most physically sounded systems, then the density contains actually basically the same information because you can reconstruct, in principle, starting from the density, all observables.
Okay, yeah. So I was aware of this kind of results, but I always found it kind of amazing. So I still find it amazing actually. But okay,
agree,
but I mean it's a theorem, so there it is. Okay, cool. That's very interesting. Thanks. Okay. Well, it seems that we have a very shy audience today, but lots of people clapping and saying thanks for a very nice talk.
Thank you.
So maybe I can ask just maybe one more question, see if we have some more from the audience. So I mean, would this thing, I mean, this density-based metrics actually be measurable in I mean, okay, in principle, I mean, in reasonable principle, let's say, or in reasonable practice, and would that be useful for anything, do you think, or is it more of a theoretical tool for
in
for
principle,
us?
you can measure. I didn't think about the density itself. Sorry, the distance itself, but you can measure in principle the density. The local density is measurable.
But for the distance you'd need to, I mean, you basically, what are you then measuring? You're measuring, I mean, you basically measure the density along a protocol that is so slow that you're convinced, you're already convinced that it's adiabatic, and then you measure it for a faster protocol and compare the two. Is that essentially what?
That is correct. But what you can also do, I mean, the adiabatic density, that can be relatively easily calculated or estimated, because it's not exact, using density functional theory. It's not exact because you have to do approximation on exchange correlation potential.
I see.
So the measure would have to be on the time-dependent density, I mean the real density of the system.
Mm-hmm.
So I would say that the other density you can calculate relatively easily, or estimate accurately relatively easily, yeah.
Okay, that's interesting. Thanks. Yeah, that makes sense. Okay, so I think if there's no further questions, then maybe we can conclude it there. But I mean, of course, if anyone has any further questions, or if anyone was too shy to speak up and wants to ask Irene something, I'm sure you can just email and ask her about whatever it is you're curious about. Yeah, so with that, let's conclude. I'll just say thanks very much to everyone for joining us once again. We're not going to have any talks on Friday, so the next talk will be next Tuesday. But I'll announce that in due course. But especially, I want to say thanks very much to Professor Irene D'Amico for a really interesting talk. Thank you.
Thank you very much. Thank you, Mark. Bye-bye.
Bye-bye.